All right. Let's talk about chapter 2 in physiology. Okay. Okay. So atoms, ions, and chemical bonds. Oops. I'm not sharing my screen. Okay. Okay. So since physiological processes are based on chemical reactions, a general understanding of chemical principles is necessary. So basically taking you through chemistry and organic chemistry in the space of 1 hour. Okay. Okay. So an atom is the smallest unit of an element. It has a nucleus with positively charged protons and uncharged neutrons. And then we have electrons that orbit, and electrons have negative charges. Okay? Okay. Electrons, for the purposes of this class, do not have any mass. So the atomic mass is simply equal to the number of protons plus the number of neutrons. So again, for the purpose of this class, a proton and a neutron have the same weight, and that is the atomic mass of 1. So the atomic mass is simply equal to the number of protons plus the number of neutrons. Okay, the atomic number is equal to the number of protons, okay, or electrons, but usually we use protons. Okay, so here is a hydrogen. That's the most simplest atom. So you have 1 proton and 1 electron. Okay, carbon is a little bit more complicated. This is carbon, or also known as C12. It has 6 protons, 6 neutrons, and 6 electrons. Okay, notice, I'm going to explain more detail here. There's 1 shell here. There's 2 shells of electrons here. Okay. Okay. So electron orbitals. Okay. Electron orbitals or shells or energy levels that surround the nucleus of an atom. Okay. So if I imaginary take a nucleus, okay, and start adding electrons, the electrons will first go on the inside shell, then the outside shell, then the outside shell, then the outside shell. Okay. So starting with the one closest nucleus. Okay, the first one closest to the nucleus only can hold 2. Okay, and then 8, and then 8, etc., etc. Okay, when we talk about life and biological elements, okay, we talk about the first couple of shells. We don't really go beyond 3 in any meaningful detail because they're not really found in living organisms for the most part. So that rule of 8 that you might have, or the called the Octet Rule that you guys learned probably in high school, is not actually real, but for purposes of biology, it applies. Okay. Okay. Atoms are most stable when their outer shell is filled. Okay, so atoms try very hard to fill their outermost shell. Okay, and once they fill their outermost shell, they are stable and becomes really hard to remove electrons from an atom that's happy. Okay. Okay. Electrons in the unfilled outer shell participate in bonding. They are called the valence electrons. When we talk about chemistry, actually, about 95% of all we ever talk about are the valence bond, like the electrons in the outermost shell doing different types of bonding and moving bonds from one atom to another. Okay. You can see this here. Okay. So hydrogen, so the number of chemical bonds we can make. Okay. If you look at this, okay, one of the things I want to point out right now is this carbon. Okay, the number of chemical bonds in carbon is 4. That's the highest, right? So you can't actually get higher than 4. Okay, in biological elements. Okay, this is the reason why everything in life is made out of carbon, because carbon can form 4 chemical bonds. So you can attach 4 different things to it instead of just 1 or 2. Okay. Okay, an isotope. The atoms of the same element, but with different numbers of neutrons. Okay, their atomic number is the same, but their atomic mass is different. So if you add a neutron, okay, you add mass, but you don't add anything to the atomic number. Okay, adding and subtract neutrons can make a nucleus fall apart. Okay, and so these isotopes are radioactive. Okay, and radioactive elements can be used in medical testing and physiological research, in addition to making nuclear weapons and all that lovely stuff. Okay. 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 Chemical bonds. Chemical bonds are formed when electrons in the atoms interact. The number of bonds an atom can form is determined by the number of electrons. So, yeah, and we just went over that in little detail there. Okay. The first type of bond is a covalent bond. Okay, covalent bonds are where the electrons are shared or physically shared. Okay, so literally when you look at it, the electron for one thing actually goes, the electrons actually go around both nuclei. Okay, and you'll see how that works a little bit. Okay, the electrons are shared equally, form a non-polar covalent bond. Okay, if these, so nuclei, they fight for the electron. Okay, if you take 2 hydrogen atoms and you put them together, one, like, they're going to be equal to each other, so they're going to fight and they'll share the electron equally. Okay, so the negative charge of the electron will be equally spread on both sides. Okay, some elements are stronger than others in terms of how much they want an electron. In scientific terminology, they have higher electronegativity. Okay, so you want the negative charge more. Okay, so it's not that they will spend all the time with the more powerful nucleus, they'll spend more time with a more powerful nucleus. Okay, a good example of that is water. Okay, oxygen and hydrogen. The oxygen, okay, is more electronegative, so it will pull the electron more toward the oxygen, and therefore the oxygen will be slightly negatively charged. The hydrogen, because it got pumped for the electron most of the time, it will be positively charged. So when you have a water molecule, you have one side that is negatively charged and one side that is positively charged. That makes it polar. Okay, so polar means the 2 sides are not equal. Okay. All right. How to get some water. Okay. So equal charge. Okay. Equal charges. Okay, these are all equal charges. All right. Sorry, there was a really loud ambulance, so I stopped the recording so it would pass, and I can actually talk in a normal voice. Okay. So, like I said, water is a polar molecule. Okay. The oxygen has a negative charge. It's not a complete negative charge. It's just a slight negative charge. That's why it's delta minus. That little weird Greek symbol right there is called delta, so negative charge. And then the hydrogens are delta positive. Okay, so now look at it. Okay, the positive charges on this side, oops, is going to be attracted to the negative charges on this side. Okay, and occasionally what will happen is one hydrogen will pop off and lose its charge completely to the oxygen, and it will form an H plus acid, and this will be an OH minus base. Okay, this happens about 1 out of 10 million water molecules. Okay, 10 to the 7th. So, okay. Okay. Ionic bonds. Okay, like I said, some electrons or some nuclei really want electrons, and some nuclei really don't want electrons. And the best example of this is sodium, okay, and chloride. Okay, so things like chloride, where it has 7 valence electrons on the outermost shell, and it only needs 8, are really, really electronegative. And if they get 1, they're set and they're happy. Okay. Sodium, on the other hand, just has 1 valence electron on the outermost shell. So if it loses that 1, then its new outermost shell has 8, and therefore is happy because it follows the octet rule. Okay, so this type of bond, ionic bond, is not an electron share, is an electron transfer. Okay, so I move 1 electron over here, and now these are equal to each other. Okay, so now I have a positive charge sodium and a negative charge chloride, and both are follow the octet rule, so they're both happy. But now look what's happening. This is a positively charged thing, this is a negatively charged thing, and they attract each other. So ionic bond. Okay. The ionic bond is they're not physically attached to each other. They're just charged and therefore attracted to each other. Okay. So ionic bonds are weaker. Okay. 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 And so the positively charged one is a cation. The negatively charged one is an anion. Okay. Okay. Most ionic compounds will dissolve, okay, when or dissociate when dissolved in water, okay, because like when you take salt and you add it to water, what will happen is the water will pull the chloride away from the sodium, okay, because the water is polar. This is what makes water such a great solvent. Okay, so you have a sodium here. The sodium, the positive charge of the sodium, is being wrapped around by the oxygen part of the water. Okay, so it actually forms these shells called hydration shells. Okay, the chloride does the same thing, but with the positively charged side. Okay, so this is why water is so good at dissolving salt. That you can add incredible amounts of salt and it will dissolve in water precisely because of this. Okay, if you try to do the same thing with oil and salt, oil isn't polar, so like this won't happen with oil. So oil doesn't dissolve salt well. Okay. All right. This is hydrogen bonding. Okay. hydrogen bonding is where the O minus here is attracted to the positive charge of this one. That one is attracted to the positive charge of that one, and that one, and that one, and then this one is attracted to the positive charge. Like, so the hydrogen bond is a weak bond formed between two polar molecules based on opposite charges. Okay, it's not only water, but water is the most obvious place where you can get a hydrogen bond. Okay, and it's responsible for surface tension. Okay, surface tension. The water wants to stay with water, so they form a nice little seal on the very top, and that is surface tension. Okay, that's the reason why insects and stuff can like run across the surface of the water. You can see it like step on water and like push the water down a little bit, but because the water molecules want to stay together, then you actually have enough strength to hold up the insect. Okay, and that is surface tension. Okay. Okay. So it forms between amino acids on the surface of protein to form a 3D structure. It actually holds the two halves of the DNA together. In the middle is literally a whole row of hydrogen bonds. Okay, hydrogen bonds are weaker than ionic bonds. Okay, they're like partial ionic bonds, and they're weaker than covalent bonds. But in the field of biology, hydrogen bonds do a hell of a lot more because there's so many more of them. Okay. Okay. I already discussed this earlier. Some water molecules ionize to form hydrogen ions or protons, or hydroxide ions, OH minus. Okay. Okay. So a neutral solution is a pH of 7. Okay. A neutral solution has a pH of 7. By definition, a pH of 7 means there's 10 to the minus 7th molar concentration of H plus. Okay. pH is the negative log of the hydrogen molecules. Okay. In neutral water, which that means there's also 10 to the minus 7th OH minus molecules. Okay. When a solution has more H plus, hold on 1 second. Okay. When a solution has more H plus than OH, is now acidic, okay, and it's called a proton donor. Okay, you can donate proton to something else. When a solution has more OH, okay, then it's called basic, or alkaline. The other term in biology is called alkaline. Okay, and it's a proton acceptor. All right. The pH scale runs from 0 to 14, with 0 being the strongest acid possible and base 14 being the strongest base possible. The pH is calculated by the log of 1 over the H plus concentration, or otherwise known as the negative log of the H plus concentration. Those two things mean the same thing. Okay? Okay, so this scale, okay, is logarithmic, which means something with a pH of 6 actually has 10 times the hydrogen atoms of something with pH 7. So pH 5 has 10 times the concentration of pH 6. pH 4 has 10 times the concentration of pH 5. Okay, so something that's pH 4 has 1,000 times the concentration of hydrogen atoms of something that's pH 7. Okay. Okay. So you can see means okay. A buffer is used to stabilize pH in a solution. Okay. So the best example is our blood. Our blood is an incredibly good buffer. Okay. We keep our pH at a very tight level. And the way we do this is we have two components, a weak acid and a weak base. Okay, so when you add acid, the acid binds to the weak base. When you add base, the base binds to the weak acid. And so it stabilizes. Okay? Okay. So in blood, two molecules stabilize the pH, the bicarbonate ion, okay, and the carbonic acid. Okay, so if you add H pluses, if you add acid, the bicarb will absorb the H plus. It will form more carbonic acid. If you add more base, okay, the carbonic acid will rip off one of its hydrogens and give it to the base, and it will form more bicarbonate. Okay. Okay. That only works to a certain level. Eventually, you run out of one or the other. And so, if the blood pH is below 7.35, the condition is called acidosis. Okay. If the blood pH level is above 4.4 or 7.45, the condition is alkalinosis. Okay. Okay. Organic molecules, okay? By definition, something that's organic has to contain two things, carbon and hydrogen, okay? Okay, so carbon can form 4 bonds to satisfy its valence shell, okay? Carbon cannot form any type of ionic bond. They only form covalent bonds, so they have to form 4 covalent bonds. Okay, so you can attach many things to it. In fact, you can attach one thing twice, and so that is a double bond. Okay, or a triple bond. Triple bonds are extremely rare, but they are possible. Like cyanide is a triple bond. Okay. Okay. So here, this is all single bond. This here, you can see these two are sharing not one pair, but 2 pairs of electrons. So you have a double bond. Okay. Okay. So carbons are not shown, but understood to be corners of the molecule. Okay. So here you see that every corner is a carbon. Okay. They also don't show the hydrogens either. So what they show everything else. Okay. So you just imagine there are hydrogens all around. Okay. And double bonds are shown this way. So you can just imagine hydrogens all around. Okay. So the way you do this, okay, look, this thing's a carbon. There's 2 bonds here that are shown. That means there's 2 more that are not shown. So there must be hydrogen here. Okay, here there's 1, 2, 3 bonds. Okay, that are shown. Hydrogen bonds to 4 things. So the 4th one must be hydrogen, and it must be here. Okay. So you can see that here as well. Okay. So here they show the carbons, but they don't show they don't label the hydrogens. Okay. 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 So carbon chains and rings form backbone for more reactive groups of atoms called functional groups. Functional groups have a function, and we'll go over the important ones. Okay. So here, okay, this. Okay. This C double bonded to an O is called a carbonyl group. Okay, you can see the carbonyl group in ketones. Okay, and you can see the carbonyl group in aldehydes. Okay, organic acids. Okay, hydroxyl group is an OH. Okay, hydroxyl groups are found in things like alcohols. Okay, sulfur groups. Okay, so hydro groups or sulfur groups. Okay, amino groups. That's an important one. Okay, nitrogen, NH2. Okay, carboxyl groups. Okay, this is a acid. Okay, this is a pretty useful acid. A lot of the acids that we use have this group right here. Okay, and then this is a phosphate group. Okay. Yeah. Okay. Stereoisomers. Okay, are molecules that have the exact same atoms, but arranged in exactly the same sequence, but they still differ in the spatial organization of their functional groups. A characteristic is critical to function. Okay, an enzyme may interact with one stereoisomer but not another. Okay, so the way to explain stereoisomers. Your left hand has 5 fingers, your right hand has 5 fingers. They go thumb to pinky, but they're different. Okay, I can fit things. They're mirror images of each other. Okay, but they're not the same. I can't put them on top of one another. Okay, does that make sense? I can't stack them. So if I have an enzyme that has a function, I can only fit this hand in, but not this hand. Okay, if someone was shaking my hand with their right hand, I would use my right hand to match. If I try using my left, it wouldn't fit. Okay. Okay. Okay, the types of stereoisomers. Okay, cis trans. Okay, cis same side, trans opposite sides. Okay, so when I look at this, okay, this is a butene. Okay, butene. I have a double bond right here. Okay, now I have 2 hydrogens and 2 big blobs, right? This thing right here and this thing right here. See how these 2 are on the same side? So cis butene. These 2 are on opposite sides, so trans butene. Okay, so how I determine cis and trans, I take a look at a double bond and I find the 2 biggest things coming off the double bond, so this one and that one, and they're on the same side, they're cis. If they're on opposite sides, they're trans. Okay, enantiomers, okay, are mirror images. Like I said, they're your hands are actually enantiomers of each other. Okay, they're mirror images. Okay. All right, we'll take a break here. The rest of it will be in part 2.